Hello, welcome to lecture 20 of CS 531 Memory Systems and Architecture. So in this week, from this week, we have started discussing the concept of main memories and the advancement in main memories. Basically, we'll discuss about the advancement in terms of reducing the refresh overhead of main memories and how to handle the row hammer attacks. These two techniques we'll discuss mainly. There are some other area also we'll discuss, but these two will be the most important areas that we'll discuss during the next 3 weeks. But again, there is a important announcement that I have also mentioned in my previous lecture. Here I am again repeating it, that if you may find during these 3 weeks there some of the lecture clips are pre-recorded. You may realize it also when you are watching these lectures. So if you find any announcement which is not fitting for this semester, then you can ignore it. Or also if I have tried to remove all this announcement and all, but if you found any announcement which you think it is not fitting for this semester, then you can always ask me that we found this type of announcement in this lecture, is it appropriate for us or not. But yes, if there is any instruction regarding which part is important for your exam, which part is not important for your exam and all, then always consider that that is valid for you also. One more important point here is to understand the concept that I will discuss from today onwards. You must have a clear understanding about the basic concept of DRAM that I have discussed before midsem, like rank, channel, bank, DIM, and different other modules of DRAM. What is called row buffer, what is pre-charge, what is activation. All these things will be required. Also, you make sure that the concept that I discussed in previous lecture, that is lecture 19, where I have explain different timing concept like TRCD, TRES, read cycle time, write cycle time. All these things will be also required for next lectures. Here I'll quickly give you a recap that I have explained in previous lecture regarding the timing constraint of DRAM.
So in today's lecture, we'll mainly discuss about the recent advancement in DRAM technology in different direction. So all these topics and the advancement happened in all these areas of DRAM will be discussed today. So let's start with the energy saving first. So DRAM consumes significant static energy, both in active and ideal state, due to continuous leakage and refresh power. Because we know that charges, informations are stored in DRAM as a form of charge, and the charge leaks. That's why you have to refresh it periodically. So the both the continuous leakage and refresh both consume significant amount of energy. That's why reducing energy consumption of DRAM is a major area of research. And to reduce the energy consumption of DRAM, sometimes these commodity DRAM design is combined with some other memory technologies, that are mainly non-volatile memory technologies, to design a hybrid memory technology. So we'll also discuss how a hybrid memory technology designed in combination of DRAM and other non-volatile technologies can reduce the energy consumption of DRAM or main memory. There is another way that can be used to reduce the energy consumption of DRAM is mainly the data compression or packet compression. There are two ways possible. One way is compressing the data before storing it in DRAM. Another way is compressing the data before transferring the data through the data bus. So we'll discuss this also. We'll discuss mainly these papers. So let us discuss first paper now. The first paper says, so in this paper, authors try to reduce the energy consumption of main memory by designing a main memory with two different technologies, combining the technology of DRAM and non-volatile memory technology. So the non-volatile memory they used here is RAM. RAM means resistive random access memory. It's a non-volatile memory technology. So the advantage of DRAM, the disadvantage of DRAM, it's consume more energy. It consume more static energy because of, as I already explained, the main reason of this high consumption of static energy is the leakage of charge stored in capacitor and the refresh overhead. And on the other hand, the non-volatile memory has almost negligible static energy consumption, but it has higher latency than DRAM, and also it has higher dynamic energy consumption. So both DRAM and non-volatile memory has some advantages and disadvantages. Also, there is one more limitations of non-volatile memory is in the non-volatile memory has a limitation in number of writes. So throughout his lifetime means it means that throughout his lifetime you can do only this number of writes in a particular cell. After this cell will be damaged. So in a non-volatile memory, especially in RAM, we have to be very serious about how many writes we are performing in the particular memory cell. So in this paper, what the author proposed is this: there will be the main memory is a combination of DRAM and non-volatile main memory, but there should be a software-based mechanism which will guide that from where to place a newly incoming data. Means if a particular application has more number of writes, then it's better to place it in DRAM, because if there is a more number of writes, and if we place it in non-volatile memory, then maybe it will create issues in non-volatile memory, as there is the write is expensive in NVM memories. So this way they design and they propose a software-based approach based on which they come before starting any application. They compare it and they analyze it, then where to place the application, either in DRAM part or in NVM part. So this is their main proposal, main idea, and their motivation was to combining the two different concepts to improve or reduce the energy consumption of main memory. The second paper is important for your course, and I'm expecting from you that you should read this paper and try to understand this paper, because questions may come in answer from this paper. And this is a very interesting proposal also. It is called tiered latency DRAM. I will explain this concept now. So this paper is called tile latency DRAM, or we will say it TLDRAM throughout this discussion. So the main idea of this paper is to reduce two time constant that is called TRCD and TRC. I hope you remember what is this two time constant. TRCD means row column delay or rest to cache delay, and TRC means read cycle delay. So they are mainly trying to reduce these two timings. So just a simple question. You can pause after this question and think by yourself there, and try to think the answer by yourself. If we reduce the RCD time, what will happen? And if we reduce the RC time, what will happen? So if we reduce the RCD time, if you remember what is RCD time, RCD time is the time taken from issuing the row activation command until the data available to the row buffer. This time is called TRCD time. So after TRCD time, the data is available in row buffer and a column read command can be issued, right? So if you reduce the TRCD time, that means data will be available in row buffer in much lesser time. So it is a advantage. And now, what is TRC time? TRC has a time has two more components. After this, the second part is read restoration. That means the data must be restored back into the row. It will take some time, and the total time is called TRES. That also I have explained in my last lecture. And after this TRES time, if the controller want to access a different row, then before accessing that row, a pre-charge command is also required. So total read cycle time is TRES plus TP pre-charge, and that time is called total read cycle time. I hope you remember it from last lecture. At this point, let us consider that the basic design is the design. For example, if there is a bank with multiple rows and there is a single row buffer at the bottom. We'll consider this design to understand the basic motivation of this paper. As I said, the main idea of this paper is to reduce these two time, TRCD and TRC. But how to reduce TRCD? Both TRCD and TRC time are mainly depend on the bit lines. If you remember the basic structure of a bank, then both TRCD and TRC are doing something of moving data from row between row and the row buffer, or row and sense amplifier. They are moving some data either from row to sense amplifier or from sense amplifier to the row. So in this scenario, the length of the bit line is very important. If the length of bit line is less, then these two latency will be less. And if the length of the bit line is very high, then these two latency will be more. In this diagram, there are three designs. Three options are given. Let's concentrate on the second option. This option. This option is the option that we have discussed in last two lectures. Where I said that a bank has multiple rows. Assume there are multiple rows here, and these are the bit lines. And at the bottom of the bank, there is a sense amplifier sharing by all the rows. This is exactly the design that we discussed. And if you see here, the bit lines are very long here. So if the bit lines are wrong, then TRCD and TRC time will be higher here in this design. Let us discuss this design. This is another design. In this design, you can see that this bank, or this there is a the area of this bank is divided into two sub arrays here, and each sub array has a sense amplifier. Now, in this design, compared to the second design, the first design has shorter bit length, right? Because this bit line is shorter because it has independent sense amplifier. Because of the shorter bit lines, both TRCD and TRC time will be reduced. So this is a better architecture in terms of latency. So if you just your only target is to reduce the latency or the DRAM access latency, then this design is better. But what is the problem with this design? The problem with the second design is consume more area because we are duplicating the sense amplifier first of all, and second is it will also consume more energy because of this additional sense amplifiers. That's why the motivation of this paper is it possible to use the advantage of this design without using a duplicate sense amplifier? That is the main motivation of this paper, and this is performed in this design, and this is their proposed design. So in this design, they have used some isolated transistor. You can see there are transistor. Or you can say there are some switches here. There is a row of switches here. So if these isolated transistors are when these isolated transistors are off, then this upper side will be cut from this sense amplifier. In this case, in this particular scenario, the bit line length of the bit line will be reduced. And when these transistors are on or these switches are on, then length of the bit line will be more compared to this smaller bit line. This segment is called near segment, and this segment is called far segment. There are two different segments now in the same bank, separated by a isolation transistors. So if we see the latency of this design, so this latency of both TRCD and TRC is given in this table. So this is the TRCD and TRC value of the first design. This is the latency of the second design, and this is the latency of the proposed design. So proposed design has two different segments, near segment and far segment. So the latencies are given for both the segments separately. So if we see from this table, then TRCD value of near segment is the lowest value, and which is same as the TRCD value of the first design, which that means the bit line is very less. So obviously the TRCD value will be low. If we see this value, TRCD value of far segment is also not very high. If we compare it with this value, this is the second diagram where the bit line is very long. The TRCD value is 15 nanosecond, but the TRCD value of far segment is 12 nanosecond only. How this is possible? It is explained in this paper later, so you can read it, and I'll show you where it is explained. That it normally it looks like that it should be same because the bit length of both the design, there's a design, there's design number 2 and the proposed design looks similar. So how this TRCD time is less here, that is explained later in this paper. But if you see the the TRC time of this far segment is more than the second design. So how this TRC time is more and TRCD time is less, that is explained in this paper. So now just concentrate on this particular values. Suppose there is a design where TRC time is less, TRCD time is less, but TRC time is more. When it will give you advantage? If TRCD time is less, that means within a very less amount of time, data will be available in row buffer. And if there are more number of accesses from the same row, that means multiple column requests from same row, then that request can be solved very quickly because the data is available. But if it has a very long TRC time, then if this consecutive data are from different rows, then in that particular case TRC time is very important, because after accessing data from one row, if we want to access the data from another row, then pre-charge time is very important. So since they have designed divided into two parts, that is the near segment and far segment, and this RC time of the far segment is better than the second design. It is giving better performance in times of latency and energy consumption both, that we will explain now. Now, before discussing more about the proposed design, let us discuss some basics of DRAM again. So, hope you remember what I said, that in a particular DRAM chip there can be multiple banks. So, this particular design, you know that in a particular chip there are multiple banks, and I told you that in a particular bank there is only one array, right? There is on one array, that means, and there are only one row buffer, but which is not true here. If you see here, a bank is divided into multiple sub arrays, and each sub array look like this. Each sub array look like a array. So in this particular paper, this is the model they follow. There are some other models also possible. So whatever I said, that whatever proposal they said, they applied in this sub area. That means the all these rows in this sub area are divided into two segments. Based on some isolated transistor will be installed somewhere in here, and based on this isolated transistor, these rows will be divided into a near and far segments. All these sections are explaining the basics of DRAM operations and all the timing constant that I already explained to you. You can read it from here, you will find it really interesting. But one important thing that I have not explained you in last class is called bit line capacitor. What I explained in last class, that how using sense amplifier we can read and write from a DRAM cell. And I also explained in my first lecture that how using a sense amplifier you can read from DRAM cell, or you can write to a DRAM cell. But at that time I have not explained in detail. I just said I have explained this, that half VDD plus delta, and after said that once it is half VDD plus delta, automatically sense amplifier will be moved to stable state 1. I said automatically, but there should be some logic behind. So that part I have not explained. So when you will study this paper, you will find there is a concept called bit line capacitor. Read it properly, then you will understand how this is actually happening. So all these things are already basic concept. These are background knowledge, not the proposed idea. And then again, this is the proposed idea. This survey is divided into two segments, far segment and near segment, and these are the isolated transistors. As I already explained, once these transistors are on, then these segments are available for this row buffer. Otherwise, when these transistors are off, then only this segment is available to the row buffer. That means bit line is reduced if the for near segment, and when these transistors are on, bit line length of the bit line will be more. So now how we can implement it, or we can use it to give benefit. So they give two different approaches. First approach, they say that near segment can be used as a cache for the far segment. That means all the important block for the far segment will be first of all stored in the near segment, same as row buffer. So this is their implementation details they've given mentioned here. They say that they can implement it in three different ways. The first is near segment as an OS transparent hardware managed cache. That means OS will have no idea about these two separate segments, and OS and in this case OS will see only the far segment. That means OS will see only the far segment as the actual capacity of this DRAM, and this near segment will be working as a hardware managed cache for the far segment. So in this case, in this case also, this particular case is divided into some other subcategories. First category is saying simple caching. In simple caching, what they are saying, there will be three types of events. First is sense amplifier hit or row buffer hit, that you know. That means when a controller want to access a row, there can be either a row buffer hit or a near segment hit. Why I'm saying near segment hit? Because in this particular case, near segment is using as a cache. So either a row buffer hit, either or a near segment hit, or there will be a near segment miss. If there is a near segment miss, then then the controller has to read the data from a particular row of far segment. So there are three events possible in simple caching. Same as a basic cache memory, there will be a replacement policy. They said that the replacement policy is LRU. So there is a LRU replacement policy managed for managing this near segment. So that if there is a access, when there is a access to a row in far segment, that row will be copied to the near segment, and the replacement is based on LRU. After this, there are two subcategories of this cache where this same near segment can be used as a cache memory. And this category, this mechanism 2 and mechanism 3 are mainly based on some selective cache storage. Will only store the important rows from far segment in the near segment, not every rows. And what do you mean by important? Important has different meaning in this section and in this section. So read it, you will understand it, what they are saying by important. And again, I am repeating the same thing, that in these two mechanisms, that means mechanism 2 and mechanism 1, sorry, mechanism 3, they are not placing every row from this far segment to the near segment. Only the important rows who are accessing from far segment will be stored in near row, and other rows which are accessed from far segment which are not important will not be stored in near segment. The second way to use this proposed design is expose this near segment capacity to OS. That means let OS know the complete structure of this sub-array. That means OS should know that there is two different sections in this sub-array. One is near section, one is, and another is far section. And now OS will remap the data accordingly, and OS will decide, okay, this particular data is accessing more rapidly, this particular data is more important, so let's put it in the near segment. This particular data is less important, so let's put it in the far segment. So in this case, OS will handle it. So at the beginning, I said that the TRCD time is less for far segment, but TRC time is more. You will find the explanation in this section. In section 4.1, mainly in this area, you'll find this explanation that how TRCD time in for of far segment is less. So read this paper completely, line by line, up to section 8, and it will give you even more clear picture about DRAM structure, how DRAM works and everything. So lastly, how it is improving. So let's see the design again, and then will conclude the paper. How this particular design is improving. So it is reducing the energy consumption because the bit line is not always lengthy. When it is not required, bit line will be less. So in this way, it is reducing the energy consumption. Plus, it is also improving the access latency, because whenever this transistors are off, then bit line will be very less. So accessing near segment is very fast compared to the other approaches. So it is reducing the access latencies. Also, if you remember that the RCD time is less here, so accessing consecutive columns from same row is faster. So combining all these things, this design is better in terms of energy consumption as well as access latency. The third paper is also very interesting, but again, I'm not expecting that you should read it in more detail like I'm saying, as I said about the second paper. This paper is important for your knowledge. So the main motivation of this paper lies in this diagram. So what this diagram is explaining is there are three lines here. First line is for energy per bit. Energy per bit means energy required to access per bit from DRAM. Again, I am repeating, energy per bit means energy required to access per bit from DRAM. This is called energy per bit. This is the bandwidth of DRAM, and this is the peak power of DRAM. So if you see, and these are the different DRAM versions. Why it is GDDR? Because this paper is mainly proposing DRAM for GPUs. That's why they are using GDDR5. So and this is the latest version, GDDR5X. So if you see, in GDDR5X as compared to GDDR5, the bandwidth increased twice x, or the bandwidth increased two times. But if you see, energy has not reduced much. The energy consumption, that means for per bit access, is almost same. It had not reduced much. So this is the problem, and that's why at this peak bandwidth here, the power consumption or the peak power is also almost double as compared to this. That means the bandwidth is increasing, this fine, but the energy consumption per bit, that is the cost per bit, is not decreasing much. And that is the main reason that power consumption is also not decreasing in DRAM, different DRAM versions. So this paper is proposed to decrease the energy consumption of DRAM, but only targeting on data transfers. So their concept here in this paper is how to reduce the energy consumption during the data communication from DRAM to the processor. So during this communication, how to reduce the energy consumption of this communication. Communication of information means either sending binary ones or binary zeros, right? So they have found that sending binary one is more energy consuming than sending binary zeros. How it is explained here, I'm not explaining in detail, read it, you will understand it. That sending binary one is more expensive than sending binary zeros. So what they have done in this paper is that transferring binary one takes more energy. Somehow they propose the encoding technique which is reducing the number of one values in the packets that are sending from DRAM to the cache memory. This is how they are reducing the energy consumption, and they claim that the energy consumption is reduced by 5.8% as compared to the baseline. So this is how you can also reduce energy consumption of DRAM by reducing the communication energy. Another similar concept in DRAM that we can use it, the compressing the data in DRAM. If you compress the data in DRAM and then store it in DRAM, then there are two advantages. First advantage is it will take less storage, and also it will take less energy. So what I'm expecting from this slide, that read this second paper properly. This is only I'm explaining. I'm not giving you much task, but at least you should read this paper, this second paper properly. That's it. Now let's move on to the second concept, that is how to reduce the access latency of DRAM. So in this slide, we will discuss some research proposal, that recent research proposal uh, for reducing the DRAM access latency. The first paper that we'll discuss is row buffer decoupling. So what is row buffer decoupling? This is explained here. In row buffer decoupling, what they mainly did in this paper, this is row buffer decoupling. So in this paper, what they mainly observe is try to reduce the pre-charging time. You know what is called pre-charging, right? So in pre-charging, there are two different things that I have not said in last class. I just say pre-charging, and you know what is pre-charging. What pre-charging means, pre-charging the row buffer as well as pre-charging the bit lines. So if you when you read this paper, you'll find that pre-charging the row buffer is very quick. The time required for pre-charging a row buffer is very less. But pre-charging the bit line needs some time. So what they propose here, that they propose that there should be some isolated transistor, same as proposed in TL DRAM. That in TL DRAM they use isolated transistor to separate the complete sub-bank into two different segments, right? Near segment and far segment. What they did here, they use this isolated transistor to separate the bit lines from sense amplifier whenever required. So for example, suppose there is the activation command given to a row, and then after TRCD time, all the informations are now available in row buffer. After this, it will take some more time for data restoration, right? So after data restoration, this isolated transistor will be off, so that the bit lines are now separated from sense amplifier. because and now the pre-charge of bitline can start. Why we are doing it? Because at this moment pre-charging of raw buffer is not possible, because raw buffer has the data, and now there will be there will be some column access command will come, and then the data should be read from raw buffer, right? So the data stored in raw buffer is important, so we cannot perform pre-charge to the sense amplifier right now, but we can start pre-charging the bit lines early because of this isolated transistor, and this is their main idea. They said that start pre-charging the bit line as early as possible, so that the total pre-charge time can be reduced. So if you can reduce the total pre-charge time, then that means it is reducing the TRC time also. That means read cycle time is reduced. So if you reduce the read cycle time, TRC time, what will happen? It will improve the access latency. I hope you are understanding all these things, because you know what is read cycle time and what is pre-charge and what is activation and all. So if we reduce the TRC time, it should improve the latency. So this is the proposal of this paper. The next proposal is lazy pre-charge. Lazy pre-charge means is also almost similar to the first proposal. That means it's also concentrating on pre-charge time. The first paper that I explained is was mainly based on how to reduce the pre-charge time. Here it is saying how to hide the pre-charge time. That's why it's called lazy pre-charge. I'm not explaining this paper in detail, but if you want, you can read it. I'll share this paper. This is mainly from how to hide this pre-charge between two consecutive row access. And this paper is TLDRAM that I have already discussed. TLDRAM is both reducing energy as well as reducing the latency of DRAM access. That's why I have also added this paper in this particular slide. Now we'll see the recent advancement in reducing the refresh overhead of DRAM. So before discussing the reducing the refresh overhead of DRAM, first of all we should understand what is the refresh overhead of a DRAM. Executing one refresh command time is called TRFC. During this TRFC time, the normal operation of this bank is blocked. That means when a refresh operation is performing in a block in a bank, the normal operation of this bank is blocked. It cannot do any other normal operation. So it is blocked. So this is the overhead of refresh. This is the first overhead of refresh. And the second overhead of refresh is the energy consumption. The refresh mechanism needs some additional energy. So these are the two overheads of refresh. All this paper that we'll discuss here is mainly how to reduce this overhead. For example, if there is no refresh, suppose there is a DRAM where there is no refresh is required. So how it will give benefit? First of all, it will never block the bank. That means the bank is always available to access. That means it will improve the access latency. Second, there is no energy required for the refresh. That means it will also reduce the energy consumption. But removing the refresh operation completely from DRAM is not possible. So all the research is mainly concentrating on how to reduce the refresh overhead of DRAM. So there will be a separate class also on this topic, how to reduce the refresh overhead, and this course I'll give more emphasis on this particular topic. So in this class I'll only explain a single research paper that is called smart refresh, which is very interesting, and most of the recent refresh technique is based on this concept called smart refresh. So before starting the discussion of this paper, smart refresh, some more concept of refresh operation should be clear. The time a cell can retain its charge after refreshing the cell is called retention time. That means after every retention time, the cell must be refreshed again, otherwise the data will be lost. So this time is called retention time, and after that means after every period, every retention time, the data must be refreshed. That means this refresh is called periodic refresh. So normally in a normal DRAM architecture, during the periodic refresh, all the cells in every rows must be refreshed, and this is very expensive, right? During this operation, the entire bank is blocked. So this paper, the smart refresh, says that it is not required to refresh every row during every periodic refresh operation. Why? Because if a row is recently accessed, that means it is already charged. I hope you know the concept, right? I have explained in my first two lectures that how when you access a row, and that means when a controller is sending activate command to a row, the row content of row will be available in raw buffer, but at the same time, after some t rest time, the row is also automatically restored. That means the row is again refreshed. So the smart refresh concept is based on this idea that if a row is recently accessed, then it's not required to refresh in the next periodic refresh operation. To implement smart refresh, the controller maintains counter for each row. So that means for each row there will be a counter in the controller, and that counter may be stored either a 2-bit or 3-bit values. And when the counter value is 0, the row must be refreshed. As shown in this figure, if you see here, in controller each row has a counter. Means this is a counter for this counter is for one row, this counter is for another row, like this, and it's a 2-bit counter. So maximum value is 3. So as I said, when the value becomes 0, this row must be refreshed. Okay, and every time when a row is being accessed, the value is again become 3. This is how smart refresh works. So now suppose the retention time of this DRAM is 64 nanoseconds. Sorry, millisecond. If retention time is 64 millisecond and the this is a 2-bit counter, so there are four possible values here: 3, 2, 1, and 0. So once this value is 3, after 16 milliseconds of time, this value should be decremented to 2. After again one more 16 milliseconds, that means at 32, after 32 milliseconds, this values will be 1. After 48 milliseconds, the values will be zeros. And once these values are 0, at 64 millisecond of time, when the retention time will be over, it will find these values are 0, so it will refresh this row, and also the counter value will be replaced as 3. So if we implement this particular concept of smart refresh, then it is not required to refresh every row during every periodic refresh, because for example, out of all this row, these three rows has been accessed recently. So if we access this row recently, so here at this time, all these values will not be zeros. These values will be something else, and these values will be either 1, 2, or 3. So this will not be 0. So these three rows is not required to refresh. Only these rows will be refreshed at this time. So this is the first advantage of smart refresh. But again, if you read this section, if you read this section, you'll see that they said this is not the best implementation of smart refresh. Why? Because maybe we are not refreshing every row at a time, but still a vast or a large number of rows will be refreshed at a time, which is again a disadvantage, because if we need to refresh a large number of rows after every periodic every 64 millisecond of time, that also it will block this bank for a longer time. So how to improve the performance? So what they did, they propose a technique like this. All these counters are divided into multiple segments, and at a time only one counter from each segment can be decremented or refreshed. So this is the initial stage at the and after 1 millisecond of time, now this second index number 2 will work here. So index number 2, since the current value of index count this counter is 2, so it will be decremented to 1. The same here also in this segment, the second index is allowed to access, then second index the current value is 2, so it will be reduced to 1, same as in this segment and as well as in this segment. So now after the 2 millisecond of time, now the third index is allowed to access. What is the third index? Third index is 1 here. So the third index is 1, so it will be decremented to 0. Same here, the third index is 1, so it will be decremented to 0 here. This third index will be decremented to 0 here, and the same here also in segment 3. So now in this uh, in after 2 millisecond, the fourth counter will be accessed. So in fourth counter, the value here is already 0. So since the value here is already 0, here after 2 millisecond, these counter, the corresponding row of this counter must be refreshed, and the value must be reset to 3. And this way it will continue. So if you see it very closely, only 4 rows, at a maximum 4 rows are allowed to refresh at a time. So during every refresh operation, only at max only 4 rows will be refreshed. So the bank will not be blocked for longer time. So this is the main advantage of smart refresh. This paper, as I mentioned it in red color, this paper is important for your course. So from today's presentation, I have given you two paper. First paper is TL DRAM and now smart refresh. These two paper are important. Please read it properly. And also there will be one or two more lectures on reducing refresh overhead. But if you don't understand the smart refresh and other basic concept of refresh operation, for example retention time, TRFC, then it will be very difficult for you to understand other papers. So read this smart refresh paper. It will clear all your basic concept of refresh, DRAM refresh, and it will be easy for you to understand other papers. The next concept that we'll discuss regarding DRAM is row hammering issue or row hammer. What is row hammer? I have already explained in class. If you remember, I said that row hammer means if there is a row, if there is a row in DRAM and the top and bottom rows of this row are accessing very rapidly, then that may affect the content of this particular row. Though this row is not accessing, but since this upper and lower rows are accessing very rapidly, then also the charge stored in the capacitor of that particular row may discharge or may damaged. So this is called row hammer problem. How to handle row hammer problem is a very interesting area of research, and there are a lot of research still going on. Though this three and two papers are mentioned here in red color, but these are not important for your exam purpose. So the paper I'll advise you to read from for row hammering is this. Please.
There is an important announcement here for the 2021 semester that the ROMR concept that I am explaining here, you no need to read the paper that is mentioned here as red color, because there will be some separate lectures specifically on ROMR attack in the third week or of this DRAM lecture series. So here you just watch this video, try to understand the paper. Also the next paper that I will explain here for Rohammer, you no need to read the actual paper, just try to understand the concept, so that when after few days when I will explain or revisit the Rohammer in detail, then at that time it will be easy for you to understand.
Memories. This is a very interesting proposal. What they did is they propose the internal remapping of all the rows and columns. So for example, the outside from outside, when the controller send a address for particular row and column, this particular address is remapped inside the DRAM. So that means the outside world has no idea that it's not a actual. The outside world has no idea that whatever the address they are sending is not the actual address of DRAM. The actual address may change inside. So this is a very interesting paper. Read this paper and you'll understand it. Why it is important? Because row hammer, I am not. It is not very important in terms of ANSEM, but it is important for your research and it is important for your term paper also if you are planning to work on this area. Row hammer is a very open area of research, and if you see this paper is from 2019. This paper is published in October 2019. That means very recent paper. The next is hybrid main memory design. Hybrid main memory design, I have already explained one paper when I was discussing about energy. That paper, let me open that paper again. This was the paper. This paper I have already explained. So they proposed a hybrid main memory design using DRAM and NVRAM to reduce the energy consumption. So this is also a hybrid memory design. There are many other hybrid memory design possible, so but I am not explaining it. And also there will not be any additional class on hybrid memory design. I am not giving much emphasis on this particular area. The next is error correction in DRAM. This is also a very interesting topic, and maybe you can consider your term paper in this area also if you have not decided it yet. Error correction in DRAM means, if as I say that after every retention period you have to refresh the row content. If the retention period is longer, then maybe you lose some data, right? If for example, suppose after every 64 millisecond of time you have to refresh every the content of this row, But suppose you are not refreshing after 64 milliseconds, you are refreshing it either after 84 milliseconds. So if you do this, it may possible that some of the cell contain some of the charges of some of the capacitor may discharge, right? So that means there will be some errors. But if you increase the retention time, it means that the number of refresh should be less. That means it is reducing the energy overhead. Also, it is improving the access latency. But it may corrupt some of the data. So in this particular situation, if you have a very interesting error connecting mechanism which can correct your some errors of this row, then it is very efficient, right? So if you have a very efficient error correction mechanism, that it means that you can easily extend the retention time. If you extend the retention time, then it will improve the energy consumption, it will improve the access latency, and also the efficient error correction will ensure that there should not be any error in the data. So that's why this particular research area is also important. And you can continue your term paper here. You can also continue your research further in this area. The next topic that we will discuss is embedded DRAM. There will be at least one or two lectures on embedded DRAM. So today I'll only explain you embedded DRAM is also called as EDRAM, and it's mainly used to design last level cache of modern multi-core processors. Since there will be a separate class on embedded DRAM, I'm not explaining it now. And DRAM as last level cache is also a part of EDRAM. And when I'll explain EDRAM, I'll also explain this. And here there are some challenges to implement the embedded DRAM as a last level cache. One of the major challenges is how to manage the tags. So if you design a larger size large level cache, obviously the tag memory or the tag storage is also very large. So how to handle those tags? So there are many options. One option is design a separate SRAM cache to store all the tags. This is one option, but that may be very expensive. So another option is use store the tag along with the DRAM blocks. So there are many different combination possible that also we will discuss. But for all these three concepts, that means embedded DRAM, DRAM as a last level cache, and the challenges of using DRAM as last level cache will be discussed in separate lectures. Okay, so that's it for today. So what is the conclusion for today? I am giving you two homeworks. You have to read two papers. The first paper is TLDRAM, that means this paper, TLDRAM, and the second paper that I said you to study is Smart Refresh. These are the most important two papers for your course. And the other paper that I said is are also important for research. If you want to continue research in this area, you can read those papers, but these two papers are important for your course. Okay, that's it for today. Bye.